everyone, my name is Ms. Ho and I am a physics teacher. In this video, we are going to be learning about the calibration of a mercury thermometer. So for those of you who are new to my videos, I am using a Jamboard because I am more of a whiteboard slash chalkboard slash blackboard kind of teacher. I don't really like to use presentations because I feel that if I use presentations with a lot of pictures and text, you'll be busy looking at the visuals instead of listening to what I'm saying, and you won't be able to see the thought processes, which I feel will really help you understand how to logically understand a particular concept. So by using the Jamboard with my scribblings, you'll be able to follow what I am saying as I'm writing it out, and hopefully that cements your understanding better. So in this lesson, we're going to be learning, first of all, how to calibrate a mercury thermometer, and secondly, how we're going to apply the formula to calculate the unknown temperature using the uncalibrated thermometer. But first things first, let's talk about why we use mercury in a thermometer. Okay, so I'm going to use the text function here because if I start writing, you cannot see what I'm writing. Let's change colors so that it's a little bit more interesting rather than just using black on a white background. So why do we use mercury in a thermometer? Now, first things first, for obvious reasons, it is because mercury is a liquid at room temperature. Because in order for mercury to be used successfully in a thermometer, it needs to be a liquid. And it is by using the thermometry of the expansion of volume that we're able to observe mercury in the thermometer. Because what happens is mercury as a liquid, it is a very good heat conductor. So when it absorbs heat, it expands and contracts very quickly. So that is the second reason. It expands and contracts quickly. So it is only when it's a liquid that we can see the expansion and contraction more clearly. If we're using solids, solids may expand and contract, but the difference is so minimal we can't actually see and measure the difference. Gases, well, you can't measure the volume of an invisible gas, correct? So that's why having a liquid at room temperature, which expands and contracts easily, is an excellent property, and that's why we use mercury in a thermometer. Also, you also need to understand that the expansion and contraction of mercury happens uniformly, which means that the expansion and contraction happens at a linear rate. So, for example, if you put it into a particular tube, we can see that the volume changes quite consistently with every 1 degree Celsius. And we'll look more into this on the next slide. Also, it does not stick to the glass wall. Because we use glass in the thermometer. And the reason why we use glass is because it is inert. So it does not react with the solutions that we would place the thermometer in. And we don't want the liquid that we are using in a thermometer to stick to glass. For example, water. If you get a piece of glass and you pour water on it, then when you lift the glass up, of course the water is going to slide off, but there will still be water droplets left behind on the glass. And if we were to use water in a thermometer, the problem is because water sticks to glass, when the water level goes up and then comes down, there will be some water droplets left on the glass wall. And that leads to incorrect readings taken because we will be taking readings where we see the water droplets. And that will not be the accurate measurement. Mercury, on the other hand, does not stick to glass. If you do the same thing with a piece of glass and pour mercury on the glass as you lift it up, all the mercury slides off. There will be no mercury droplets left on the glass. And because of this property, it is also useful in determining the accurate level of mercury inside the thermometer. And it goes without saying, of course, because mercury is a metal, it is a good heat conductor, which explains why it expands and contracts so well. We'll make this a bit larger so that you can see. Alright, so now let's go into the next slide. Now let's talk about calibration. So the term to calibrate in this case means that we want to put a scale on a thermometer. Imagine that we have a thermometer that's blank, so there's no scale, no readings on it whatsoever. And obviously, if you don't have a scale on it, it is pretty useless, right? It's like, yeah, you put it into the solution, you're like, okay, the mercury level has changed, but I have no idea what the number is. Completely pointless, right? So imagine we have this kind of thermometer and we need to calibrate it. So if you're wondering why do I need to learn this, because in the future, if you were ever to come up with your own measuring instrument, you would need to understand how to calibrate it and why. So in this case, let's say we have a blank thermometer. So first things first, let's talk about the construction of the thermometer. Let me use another color so that it's prettier. Let's use green. So this is of course the bulb, which is where the mercury is stored. And we have the glass tube on the outside, which protects the capillary tube on the inside. So the capillary tube is the inner tube, which is extremely narrow, and this is where the mercury would go up and down. So it is the volume of the mercury that changes, but because we place it into a capillary tube, as the volume changes, we will be able to see, although we will be able to measure the length more correctly. So this tube which contains the mercury, as the mercury goes up and down, where the mercury goes up and down, we call that the mercury column, because it's vertical, right? So the capillary tube holds the mercury column, and yeah, we'll talk about the measurements in a moment. So what happens is we place the bulb into the solution, which we want to measure, and as the mercury absorbs or releases heat energy, the mercury goes up and down the capillary tube, which means the mercury column would go longer or shorter. Now, let's say we want to calibrate the thermometer. So the best thing to do is to get another thermometer with an accurate scale and put these two thermometers into liquids with known temperatures. For example, we get these two thermometers, we place it into a beaker, like, oh, okay, this solution is 40 degrees Celsius, and wherever this uncalibrated thermometer, the column goes up to, you take that marking, you mark that, okay, that's 40 degrees Celsius, and you do the same thing a few times with other temperatures. That would be ideal. That would be the most accurate way to calibrate. That's how we can come up with an accurate scale. But let's say we do not have another thermometer, and you're like, okay, this is all I have. Uh-oh, what now? So, if you do not have another thermometer, the most accurate way in which we can calibrate this thermometer is to place this thermometer into two situations where the temperature is fixed. We know it for sure, we know the temperature is accurate, and they're very easy to obtain. So one of it is ice. So I've got two pictures of empty beakers here. I'm just going to sketch just for your understanding. So let's say we put some ice in here. Now, ice on its own is not a known temperature, but we do know the temperature of melting ice. Ice can be any temperature below its freezing point, right? It could be -10, -200 for all we know, but specifically when ice melts, it melts only at 0 degrees Celsius. Of course, we're talking about pure ice in this case. Let's assume that it's all pure at this point. Pure ice melts at 0 degrees Celsius. So if we were to get some ice and it starts to melt, so I'm going to write here melting ice, and we get a thermometer. For the sake of your ice, I am going to draw using this tool instead of drawing freehand. Let's imagine this is the thermometer, right? So if this were the thermometer, you'll find that, okay, the mercury column, of course, doesn't extend very far, but because this is melting ice, and we know ice melts specifically at 0 degrees Celsius, then where the mercury column goes to, we can make the marking, okay, this number, we can mark it as 0 degrees Celsius. Now, let's put this number onto this diagram over here. Now, remember that 0 is not the lowest temperature which mercury thermometers can measure. It can go below. In lab thermometers, you'll find that the range normally ranges from between about about -10 or -5 to about, say, 510 degrees Celsius. So there is still a length of mercury column below 0. A lot of students think that, oh, at zero, it doesn't expand. That's not true. Go and check your lab thermometers if you don't believe. So wherever the column expands to, let's say it stops about here, what you do is you take a marking, you label here, this would be 0 degrees Celsius. So now you're getting the idea, right? So we know that ice melts specifically at 0 degrees Celsius. What other temperature do we know that's easy to obtain? That's right, boiling water. We know that water boils specifically at 100 degrees Celsius. So we get some water, and this time we place it over a Bunsen burner. I'm just going to draw arrows here as the symbol for heat, and it starts to boil. Okay, so this should be boiling water. If we take the same thermometer, just copy and paste this, what happens, of course, is the mercury column is going to expand. And wherever it expands to, that was not a straight line. Let's try that again. This would, of course, be 100 degrees Celsius. Now, another way to ensure that we get the numbers very accurate, because some people are concerned, like, what if it touches the solution or the ice that's not exactly 0 or 100. So sometimes instead of placing it into the beaker with the melting ice and the boiling water, you'll find that some books do suggest this. Instead of placing it into the beaker with melting ice, I'm sorry to bend my drawing this time. Okay, if we get a funnel, and of course we have a beaker underneath to catch the water that has melted, but we place the ice inside here as the ice is melting. This is where we would place, of course, the thermometer. This way, the thermometer will be in contact only with the ice that melts, because it won't be in contact with the water that has melted. Likewise, for boiling water, what we do is we put the boiling water in a closed flask, and the thermometer is suspended in the air, so that it's only measuring the temperature of the steam, because we know that steam, in this case, will be 100 degrees Celsius. So here's another method. In both cases, they are pretty much based on the same concept. You are still putting the thermometer into two situations where the temperatures are known for sure. So one would be 0 degrees Celsius, and the other would be 100 degrees Celsius. So it is for this reason that 0 degrees Celsius is also known as the ice point, and the 100 degrees Celsius mark is known as the steam point. So because these two are fixed values at known temperatures, these 2 points are known as fixed points. Sometimes we don't call them ice point and steam point. This is also known as the lower fixed point. Oops, let me just move this out of the way. And the steam point, obviously, would be known as the upper fixed point. So these are just names or terms given to the points that would help us obtain the calibration of the thermometer. So once we know this, that, okay, we've got the markings, but what next? We still don't have a scale, correct? So let's come back to the properties of mercury, and let's focus on this property. The uniform expansion is what makes mercury an excellent liquid to be used in a thermometer. Because it expands uniformly, we can now confidently make the markings between 0 and 100. So which means that measure the length between 0 and 100, and we will now divide it into 100 equal spaces, and that would serve as our scale on this thermometer. So this is a diagram I've taken from physicsclassroom.com just to show you how the markings is made on the thermometer. So we have the thermometer placed in melting ice, that temperature will be 0 degrees Celsius, and that's the marking we have. Take the same thermometer, place it in boiling water, that temperature is 100 degrees Celsius, and that would be the marking over here. Divide this equally into 100 spaces. Take that same scale, and then you can extrapolate it beyond 100, and 0. So now, of course, if we want to solve questions in our examinations based on word problems, we will not have the actual physical uncalibrated thermometer. So how do we solve the word problems? So typical word problems would involve the use of a formula like this. So this is the formula in question. This is theta. So let's imagine now that we have this thermometer. We're going to calibrate it, and then we're going to take this thermometer to measure an unknown temperature of a solution. So first things first, of course, we need to calibrate it. So once we've done the calibration, we would make the marking. Okay, let's say about here, this would be where 0 degrees Celsius would be. Now, when we want to solve questions using this formula, it would be based on the length of the mercury column. Although it is the volume that expands, but we don't measure volume because it's a little bit difficult. So instead, we have the mercury in a very narrow capillary tube, and because it's so narrow, you can actually see the length changing. It will be easy for us to measure the length of the mercury column, provided the capillary tube has uniform diameter. So that's why we are using length instead of volume in this case. So L0 in this case refers to the length of the mercury column for the 0 degrees Celsius mark. We would measure it from the bulb. Now, a lot of students think that when it's 0 degrees Celsius, there's no length. Because I keep thinking 0, but that's not true. Remember that the mercury column can drop below 0 and go above 100. So which means that there are still markings available below 0. So L0 refers to the length of the mercury column for 0 degrees Celsius from a starting point that we fix. So we take the starting point roughly about the bulb, and we would measure the length of the mercury column like so. So I'm just going to make a marking here so that's a bit easier for you to see. This is for L0. So L refers to length of the 0 degrees Celsius mark. And then we place into boiling water, so that's where we can mark the value for 100 degrees Celsius. So L100 refers to the length of the mercury column for the 100 degrees Celsius mark as we measure it from the same starting point as for L0, as you can see. And this, of course, would be L100. So, like I said, we take this thermometer now and place it into an unknown temperature, and we would like to measure that particular temperature. So, let's say that unknown temperature is, let's say about here, say, and we'll make this, and we'll label it as theta. And L, theta, of course, refers to the length of the mercury column for this particular temperature, again, measured from the same starting point. It has to be from the same starting point, okay? Over here. And this would be L theta. So once you understand how the length is obtained, it is a matter of substitution. But let me explain this a little bit more so that you can understand why this formula looks so complicated. It is not complicated, it's actually quite easy. In the end, it is all about comparing to the baseline of 0. And here's what I want you to understand. Because mercury expands at a uniform rate, this formula is actually derived from the comparison of two ratios. The ratio of the temperature change to the ratio of the length change. Because remember, mercury expands at a linear rate. For every 1 degree Celsius, that change is uniform. And that's why this works. So how's the comparison? Just think of it as everything needs to be based on the 0 degree Celsius mark. Come back to 0. So what happens here? Let me just draw a line for your visualization. Everything comes back down to 0. So let's just make the marking here from theta. And okay, let's just use this color black to 100. So you see, right? This is between theta and 0, and this is between 100 and 0. So we are comparing, whoops, that's good. So we are comparing theta to 100, and this ratio would be equal to the length between theta and 0. So you see, this part of L theta minus L0 is actually this. L theta minus L0 would be this yellow color mark. This would be, let me write it here, L theta minus L0. That's how we get this equation on the top. So the L theta minus L0, and compare this ratio to this black line. Let's put it here this way. L100 to L0 is what? It's actually L100 minus L0. Can you see? So this is actually L100 minus L0. And that's how we get this equation at the bottom of the fraction. And that's where we get L100 minus L0. You see this ratio? So remember that for ratios, we can convert this into fractions. So I'm going to do that. Theta over 100 equals to L theta minus L0 over L100 minus L0. Then we bring this up and bada bing, bada boom, and ta-da! And that's how, whoops, this formula, okay, that looks terrible. Let me do that again. And that's how this formula was derived. So you can choose to use this formula as is when you are solving the questions. But if you don't want to memorize the formula and your mathematical foundation is very strong, then what you do is you base it on the ratio of the temperature change to the length change. You have a length of change? Let's say we got that. Length change. So, sometimes what I find helpful is to actually draw the skeleton out. Let me show you an example of what I mean. So let's take a look at the question. So we've got this. The length of a mercury column in an uncalibrated mercury thermometer is 3 cm when its bulb is immersed in melting ice. When the thermometer bulb is placed in steam, the length of the mercury column increases to 28 cm. What would the temperature be if the length of the mercury column is 23 cm? I'm going to show you two ways to solve this question. In the end, of course, they come down to the same answer. It has to be the same answer, but I'll show you both ways. First method is to use the formula as is. I'm going to rewrite the formula here. Let's use this color. Theta equals to L theta minus L0 over L100 minus L0 times 100 degrees Celsius. So, of course, you need to extract the information from the word problem. So, I'm going to underline this. We have 3 cm when it's in ice. That means that this is L0. And then we have steam at 28 cm. That means this would be L100. So they want to find out what the temperature is when the mercury column is 23 cm. This is the unknown temperature. That means this would be L theta. So substitute the numbers. We will have 23 minus 3 over 28 minus 3 times 100 degrees Celsius. You would get 20 over 25 times 100 degrees Celsius, and that's where you get 80 degrees Celsius. Ta-da! And then you got the answer. So this formula is not provided in the formula sheet if one is provided in your examination. So which means that you'll need to memorize it. Now, if you don't want to memorize it, and like I said, your mathematical foundation is quite strong, let me show you another way to solve this without memorizing the formula. I'm just going to draw a line here just to separate the answers. This is the other method. Here's what I normally do, and you can follow this method if you like. So I like to draw a skeleton of the mercury thermometer here just for my own visualization. Here's the mercury column, okay. And this is what I do. I would take the numbers from the word problem and put it onto the mercury thermometer skeleton. So I'm just going to use a different color so that you can visualize this as solution, a different method of solution. So we'll take the numbers from the word problem and put it onto our skeleton of a mercury thermometer. So starting with melting ice, that would be 0 degrees Celsius. And the length here is 3 centimeters, and we have 100 degrees Celsius, which is 28 cm. So let's make the marking here. So this would be 28 cm, and we have the unknown, which is theta. I'm just going to put a different color here so that it shows up. And this would be 23 cm. What we need to do is we need to get the ratio of the temperature to the length. So I'm going to write it this way using symbols. So the ratio of the change in temperature would be equal to the ratio of the change in the length. So I'm going to draw some arrows here just for visualization because I find that it does help. So we have, let me draw it over here. So this is for theta, and this would be for, that's not a line, and this would be for 100. So I'm just going to write this as for theta and this for 100. So what we have here is theta to 100. So I'm going to put that straight away into fractions, theta over 100. Then this length, let's take a look. This length should be 23 minus 3. So this would be 20 cm. So I'm going to put that straight away as 20 centimeters. And then for the 100, let's see, it's what, 28 minus 3, that would be 25 cm. So then from here, I can solve it as theta equals to 20 over 25 times 100, and that's how we get 80 degrees Celsius, and ta-da! That's how you get the answer. So of course, if this method doesn't quite work for you, because this is an understanding of how ratio works, and if you can't quite remember or quite understand how to do side-by-side comparisons, that will be a lot safer if you use the formula. So then we utilize the formula. So this is how mercury thermometers can be calibrated and how we solve word problems involving uncalibrated mercury thermometers. I hope you found this video educational and helpful. If you like this video, remember to click like. Of course, subscribe to my YouTube channel, Physics ROX, to get updates on more videos of physics lessons just like this. Happy studying!